Okay students, so in this class we'll discuss the mind map for the potential difference. So as you know that we have done the basic definition of a potential difference, that is the potential difference between the 2 points is nothing but the work done to bring the charge from A to B against the electrostatic force of repulsion. So that is potential difference VB minus VA is nothing but the work done to bring the charge from A to B upon Q naught, or simply your definition for your work done is equal to W by Q. So for the 1 marker children, you have to remember the formula very well, and from there you can get the formula. It's a V is equal to W by Q, or W is equal to V into Q, which is very important, and this is very important from the 1 markers. Okay, sometimes it doesn't click you, and the work done is nothing but this is the also equal to energy. So you can say that energy is equal to V into Q. Sometimes the 1 markers can be asked, like the charge say 1 coulomb is moved from the potential difference of say 5 volt. So what's the formula you are using? W is equal to V into Q. Or again this can be put in another way, that what is the energy gained by charge, say charge of 1 coulomb when it is moving through a potential difference of 5 volt. So your answer will be simply 5 joule. Alright, so this is the formula. You must memorize that W is equal to V into Q, or V is equal to W by Q. And the next important characteristic is that W is a potential difference, it's the scalar quantity, and its SI unit is volt. The next we have done the potential due to a point charge. So what is potential due to a point charge? It's KQ by R. And we have done the electric field in the previous chapter. What's my electric field? My electric field, it's a vector quantity, and that is equal to KQ by R square. So again the comparison can come to you. That is how you can compare the potential and electric field due to a point charge. Potential and electric field due to a point charge. So as you can see, potential is inversely proportional to R, and energy is and electric field is inversely proportional to R square. So if you have to plot a graph, again the graphs are very important children in the 1 marker. So if you have to plot the graph, that is both the graphs, your E and V on the same graph. So you can see that you have to plot it like this. That means my E will fall faster as compared to potential difference. You have to keep it in mind, the graphs that can be asked, and solely that depends upon if you remember the relation that V is equal to KQ by R, whereas the electric field is inversely proportional to R square. The next we did in this chapter was potential due to a dipole on its axis and on the equatorial point. So as we have learned that potential on the axis is nothing but Kp upon R square minus A square, where P is the dipole moment, R is the potential at any point, and A, that is the 2A is the length, so A is half of that. And what was a special case? When the R, that is the point at which you're finding the potential, was far greater than A, then my potential was Kp by R square. Alright, so this children, you have to learn the formulas, they should be on your tips, and on the equatorial point the dipole is 0. Alright, again from here the children, the question can come, as they're already in my video if you have seen the 1 markers, that they generally ask you if they have to move some charge on the equatorial point. So what is the work done? As I told you, what is the work done? Work done is equal to V into Q. Now at the equatorial point your potential is 0, so your work done will also be 0. From here, you have to keep it in mind, this is a very important concept, and the 1 markers can be asked. So on the equatorial point my potential is 0, so no work will be done in moving the charge on the equatorial point. And if we discuss the general case, that means if you are taking the R and theta into consideration, then my potential difference at any point, general point, was Kp cos theta by R square. Fine, this is and then you apply the special cases when theta is 0. When theta is 0, that means my P and R in the same direction. So theta is 0, that means my cos 0 is 1. So you'll get this, that is the axial line. So B is equal to Kp by R square. And if you put theta is 90, that means the angle between P and R is 90. So that is my equatorial point. So potential is 0. Then, so now you can compare the next important 1 markers are, you have to compare the potential due to point charge and due to dipole. As you've seen that the potential due to point charge is inversely proportional to R, and potential due to dipole is inversely proportional to R square. That it depends upon R. potential due to point charge only depends upon R, whereas the potential due to dipole, it depends upon R as well as the angle between R and P. And then the symmetry, you can say that. What is the symmetry for the potential due to point charge? It's cylindrical, whereas the potential due to symmetry of the dipole is your, the potential due to, this is just interchange, students. The potential due to the point charge is spherical, and potential due to dipole, it is cylindrical. So this is just interchange. All right. So this is all about the potential and the potential difference.